All right, now we'll move on in organometallic chemistry and we'll talk about bigger and possibly better alkenes. In the last slide, we talked about this complex, which is a tungsten center with 5 CO ligands and one coordinated ethylene molecule. So tungsten 0 is D6, 5 COs brings 10 electrons, and one CC double bond brings 2 electrons for a total of 18 electrons. Well, organic chemists are able to prepare all sorts of other types of donors that have linked double bonds. And so here we have 1,3-butadiene, where we have 1,2 double bonds. Benzene can be thought of, and it works well in these organometallic complexes actually, to think of it as 135-hexatriene. It can act as a 6-electron donor. We have cyclooctadiene, so it's a diene, so it can give both of its double bonds to a metal center. And then finally, cyclooctatetraene, which has 1, 2, 3, 4 pi bonds that it can donate, so it can donate up to 8 electrons. So up to 4 electrons for butadiene, up to 6 for benzene, up to 4 for cyclooctadiene, and up to 8 for cyclooctatetraene. Well, I've been very carefully saying this up to part, and we'll see here in a second why I've said up to rather than that's how many they donate. So for these first couple, we have benzene is a neutral molecule. The whole complex is neutral, and so that means that we have chromium 0. Chromium 0 is D6, it's from the 6th column. We have 2, and we'll get to this notation on the next slide. This means that all of the carbons of each of the benzenes are attached to the metal. This is an eta-6 benzene, there's 2 of those, and so it's donating a total of 6 pi bonds or 12 electrons. So 6 plus 12 gets us up to 18. Here's a really common starter complex in organometallic chemistry. This tricarbonyl iron 1,3-butadiene. Everything here is neutral, and so this is iron 0. Iron 0 is D8. We have 3 COs to give us 6 electrons. That brings us up to 14. And then the butadiene is donating both of the double bonds, and so that's 4 more electrons to get us up to 18 electrons. Both these are 18 electron complexes. This one is often referred to as a sandwich complex, where the chromium here is the meat, and then the 2 benzene rings are the pieces of bread. All right, so we do at times need to talk about something, though, referred to as hapticity, and that's how many of the atoms on the ligand are attached. Well, here's 2 sort of different cases where we can run into that. We have cyclooctadiene. Cyclooctadiene has 2 double bonds. Both double bonds here are attached to the iron center. And so this is called eta-4 because this carbon, this carbon, this carbon, and this carbon, those 4 carbons are all attached. So an eta-4 cyclooctadiene is donating 4 electrons to this iron center. So over here we have cyclooctatetraene, this 8-membered ring, which could donate up to 2, 4, 6, 8 electrons. However, in this particular complex, that would make it be over 18 electrons. And so cyclooctatetraene, when it's in this complex, is bound also eta-4. This double bond and this double bond are attached, and the other 2 double bonds are just flapping. They're just moving out in space, flapping out into the solvent. So these 2 are very firmly attached to the ruthenium center. These 2 are rotated out and away from the ruthenium center. So this eta notation tells you how many atoms are attached from a ligand. Okay, and so we can run into scenarios like this. So we have an iron center, we have 4 carbonyls, and we have an eta-2 cyclooctadiene, and let's do the electron count for this. So all the ligands are neutral, the complex is neutral, and so this is iron 0 that we have here. Iron 0 is a D8 metal. COs are easy, 1, 2, 3, 4 COs contribute 8 electrons. And then 1 double bond from cyclooctadiene gives us 2 more electrons to bring us up to 18. And I wanted to specifically show it this way because even though it may feel like, well, you've got another good donor here, why doesn't it just clamp down onto the metal? Well, if this became eta-4 cyclooctadiene, that would be a 4-electron donor, and then we would have a 20-electron complex, and that's a bad situation. That's like having 10 electrons around a carbon instead of 8. So this is a bad situation, and so the organic group rotates such that it only coordinates one of the double bonds to the iron center. So here's that ruthenium again. So the ruthenium, all the ligands are neutral. The cyclooctatetraene is neutral, and so this is ruthenium 0. Ruthenium 0 is D8. 3 COs bring 6 electrons, brings us up to 14. And here we need exactly 4 electrons. So we coordinate 2 of the double bonds, and having it eta-4 cyclooctatetraene brings us up to 18 electron complex. Okay, here's another example. What's the hapticity of cyclooctatetraene in CrCO3CO2 ? So this would be a type of question that I would ask you. I would give you this, and I probably would even give you the ligand, so you wouldn't necessarily have to know this, and I would ask you to do the bottom part of the slide here. And so you want to do the parts that are easy. So everything's neutral. So this is chromium 0. Chromium 0 is D6. That contributes 6 to the count. COs are easy. 3 COs contribute 6. And so we need to get 6 electrons from cyclooctatetraene, which could donate up to 8. And so what it's going to do is it's going to form eta-6 cyclooctatetraene. It's going to coordinate to attach to 1, 2, 3, 4, 5, 6 of the atoms. So this double bond, both carbons of this double bond, both carbons of this double bond, and both carbons of this double bond is 6. And this is the actual structure. Someone got a crystal structure and looked at it. And you see, it doesn't want anything to do with that extra pair of electrons. The organic group is rotated up and away, and so they're nowhere near the chromium center, and the chromium is binding to 6 of the 8 pi electrons.